4.4 million years ago, big brains appeared on Earth, bringing with them the ability to store more data and process more complex concepts into knowledge. In a way, the entire history of mankind represents the footprint of our ever-expanding volume of knowledge. With each new day, scientific discovery expands the boundaries of our knowledge further and further outward. Think of our knowledge as a circle or a sphere. The sphere has a surface. As that sphere expands, its surface area expands. That surface area pushes up against the unknown. The effect is that the more we know, the more we are aware of what we don't know. Venture a little further out from that boundary, though, and we begin to see where there is a vast sea of unknown that extends far beyond our own awareness. If you think about the trajectory of mankind's knowledge, it becomes clear that the largest contributing factor made possible by big brains is collaboration. The ability to work together as a community to discover new things and share the knowledge. The materials science community represents a microcosm of these concepts. All over the world, materials scientists conduct research using large volumes of diverse, multivariate data, such as crystallographic data, thermodynamic data, phase stability data, and more. Over time, scientists accumulate this data in corporate and public databases, continually expanding knowledge in a cycle of data usage and data accumulation. However, the current state of process and technology presents numerous barriers to full collaboration. When seeking data for their research, materials scientists find it difficult to reach beyond departmental, corporate, domain, and even political boundaries. In other cases, the value of data is diminished due to quality issues, non-standard and proprietary formats, conflicting data definitions, and a lack of provenance. This current state causes duplication of research efforts and research data, driving up costs, delaying time to market, and even stagnating the development of new materials and technologies. iNovex Information Systems seeks to disrupt the current state by creating a global semantic web of linked materials data. Headquartered in Hanover, Maryland, our core competencies bring the necessary forces to bear: semantic technologies and a service-oriented architecture to build a federated, decentralized web of linked data. Big data capability to process large volumes of streaming, batch, and archive data. Cloud analytics to organize, enrich, and visualize big data. And cybersecurity to preserve data integrity and protect proprietary assets. iNovex teams with industry leaders around the globe to extend the boundaries of scientific data. In Cambridge, Massachusetts, iNovex teams with Cambridge Semantics to bootstrap industry-proven semantic capabilities into our solution. Cambridge Semantics has led the industry for more than 10 years with their popular ANSO platform. In Brisbane, Australia, iNovex teams with the University of Queensland. In 2011, Dr. Jane Hunter and the UQ Fusion project team developed MatOnto, an upper-level domain ontology for materials design, and MatSeek, a search and discovery tool for integrated databases. Together with the UQ, iNovex will extend this platform to create the MatOnto semantic web and add tools for linking specific materials subdomains, including extreme materials for hypersonics. In the United States, iNovex teams with Penn State University to extend ontological development to materials with nickel-based superalloys as the model system. Dr. Ziku Liu is the director of the Center for Computational Materials Design, and he coined the term materials genome, now used for the Materials Genome Initiative sponsored by the White House to accelerate the discovery and deployment of advanced materials systems. We will work with Dr. Liu to link the nickel-based superalloy subdomain into the MatOnto semantic web. In Menlo Park, California, iNovex teams with Not-for-Profit Research Institute, SRI. World-renowned for their successful commercialization of ubiquitous technologies such as the computer mouse and Siri personal assistant. iNovex will work with SRI's Materials Design Lab to link turbine blade coatings to the MatOnto semantic web. The scientific community can build on this core capability to extend MatOnto to additional material domains, creating the global semantic materials web. iNovex will work with our teaming partners to develop an extensible ontology architecture. We begin with a Dolce upper-level ontology, which has been extensively validated through numerous applications and has ongoing support and maintenance. We'll leverage the UQ MatOnto domain ontology to describe core properties associated with materials. We will leverage proven independent ontologies for related topics such as time, measurement, and more. Working with our teaming partners, we will begin to develop subdomain ontologies for the 3 classes of materials previously cited, and then extend them to specific data structures that support those classes. MatOnto will leverage the W3C semantic web construct as the means to integrate isolated data to form intelligent, machine-understandable context. This construct provides a layered set of technologies. The foundation is built on universal and internationalized resource identifiers that uniquely identify data resources. The resource description framework provides the baseline for linking data to form the semantic web. RDF is a graph structure for representing machine-understandable information on the semantic web, and uses XML, among other formats, as a serialization method. The RDF query language, Sparkle, supports unambiguous queries which can be distributed to multiple Sparkle endpoints for computation and results analysis. Together, OWL and RDFS combine to provide publication tools for the semantics of schemas. OWL provides the abstract syntax to develop heavyweight ontologies that describe content relative to other entities and concepts within a domain of interest. This establishes semantic meaning. RDF schema provides basic logic primitives for writing lightweight ontologies that define classes of resources, organize their hierarchies, and add more intelligence to the data. The rule interchange format provides the framework for encoding knowledge as first-order logic, used to implement inference engines that process conditions and draw conclusions. The unifying logic layer applies high-order reasoning over result sets. The proof and trust components use provenance models, such as the W3C prob ontology, to provide explanations about results and their sources, including information about entities, activities, and the people involved. The provenance ontology supports assessments about quality, reliability, and trustworthiness. Cryptosecurity may be applied throughout the stack using industry standards for protecting data and services. The W3C web construct supports a host of interfaces and applications for visualizing enriched, semantically linked data. iNovex will design MatOnto, a fully decentralized, community-maintained software platform. We will release it as free and open license software, including the bootstrapped components from our teaming partner, Cambridge Semantics. Downloadable from the matonto.org wiki, out of the box it provides an on-ramp for matonto.net semantic web, data security and access controls including data licensing capability, subdomain and data store ontology editors, data ingestion and RDFizer tools, an RDF data store, interactive search and discovery tools, and presentation services. In addition, we will fully document and publish open APIs to establish a framework for add-on commercial products and services. iNovex will build and maintain a MatOnto marketplace for offering add-on commercial services and products such as ontology management, vocabulary tools, quality tools, cloud analytics, data enrichment, and more. iNovex Information Systems supports the Materials Genome Initiative by building a free and fully open semantic web for materials design and development, accelerating the discovery and deployment of advanced materials systems. 4.4